A moonless night. You find the Big Dipper, follow the two pointer stars up, and land on one steady point of light. Every other star wheels around it. This one just sits there. That's the promise of Polaris. Reliable, unchanging, the one thing in the sky you can actually trust. Astronomers have spent 2 centuries quietly proving that promise is a lie. And this time, we're not stopping at something weird is going on. We're naming exactly what's broken and why. Start with the basics. Polaris is not one star, it's 3. The bright one you actually see, Polaris AA, is a yellow supergiant, 5 times heavier than our Sun and 46 times wider. Placed in our solar system, it would stretch more than halfway to Mercury. Orbiting close to it is a smaller companion, Polaris AB, discovered only through subtle wobbles in its motion in 1929. We didn't even get an actual image of it until 2006 thanks to Hubble. And swinging far out, once every 40,000 years, is Polaris B, first spotted through a telescope by William Herschel back in 1779. 3 stars bound by gravity, mistaken for 2 centuries as a single fixed point of light. Here's where it gets genuinely strange. You'd assume pinning down the distance to the brightest star in the northern sky would be simple. It isn't. Polaris AA is so bright it saturates spacecraft detectors. Even Gaia, the most precise star mapping mission ever built, can't get a clean parallax reading on it directly. Astronomers have to measure the distance to its faint companion, Polaris B, instead, and infer the rest from there. Estimates for Polaris have ranged wildly over the decades, from around 320 light-years to over 800. The current best figure, anchored to that dim companion, sits at roughly 447 light-years. Think about that. We're using a fainter, less interesting star to measure the most famous star in the sky, because the famous one is too bright to look at properly. And even Polaris B isn't simple. It looks brighter than a star its size should, which means it might be its own hidden binary, a small mystery riding on the back of the big one. Why obsess over one number like that? Because Polaris isn't just the North Star. It belongs to a rare class of pulsating stars called Cepheids, stars whose brightness rises and falls on a fixed, predictable schedule. In 1908, an astronomer named Henrietta Leavitt discovered that a Cepheid's pulsation period reveals its true brightness. And true brightness, compared to how dim it looks from here, reveals distance. That single relationship became the backbone of the cosmic distance ladder, the method astronomers use to measure everything from nearby star clusters to the expansion rate of the entire universe. Right now, 2 independent methods for measuring that expansion rate disagree. One gives roughly 73 kilometers per second per megaparsec, the other around 67. That gap keeps growing instead of closing as more data comes in. Cepheids sit right at the center of that argument, since they calibrate one side of it, which makes it a real problem that the closest, brightest, most heavily studied Cepheid we have refuses to behave itself. For 150 years, Polaris pulsed roughly every 4 days, and that period was climbing fast by 4.5 seconds every single year. Then in 2010, without warning, it reversed. It's been shrinking ever since, and nobody has a confirmed reason why. Its brightness swings have done something no other Cepheid has ever shown. They shrank steadily through the late 20th century, flattened out through the 1990s, then started climbing again around the year 2000. Astronomers have floated theories. Maybe Polaris is shedding mass through stellar winds, at a rate some studies place near 2 septillion kilograms a year, enough to nudge its pulsation off course. Maybe it's simply caught in an unfinished evolutionary phase between 2 stable states. None of it fully fits the data yet. In 2024, the mystery deepened further. Using the Kara array, a set of 6 linked telescopes acting as one enormous eye, astronomers finally imaged the surface of Polaris directly. They found spots, bright and dark patches that shifted and changed over time, the kind of feature usually tied to a strong magnetic field pushing through a star's outer layers. That same study revealed Polaris is about 50% more massive than earlier estimates suggested. A star we've watched for centuries, and we were still wrong about its weight by half. Then, earlier this year, an even bigger piece landed. For over a century, nobody could measure how fast Polaris actually spins. Its pulsation drowns out the usual signal completely, but a team monitoring the star's magnetic field with a telescope in Hawaii, tracking it for 5 straight years, finally caught something no one had ever measured on any Cepheid before, a rotation period. 100 days, almost exactly, is the first time any Cepheid's spin has ever been directly clocked. The magnetic field itself is ODD2, tangled and complex, rather than the clean, simple pattern you'd expect from an old, settled star, yet stubbornly stable across roughly 460 pulsation cycles and 18 full rotations. Here's the part that should unsettle you. When the team compared that new rotation axis to the orbit of Polaris's inner companion, the two didn't line up, not by a little. The spin axis sits tilted at least 19 degrees off the orbital plane, and the numbers suggest it's likely closer to 55. Stars that form together as a pair spin in alignment with each other. Polaris doesn't. Something knocked its axis askew, and whatever it was happened a long time ago. That tilt slots into a bigger puzzle astronomers have circled for years. If Polaris AA and its companion B form together, they should share the same age. They don't, not even close. Polaris AA looks barely 50 million years old. Polaris B looks over 2 billion. One explanation astronomers keep returning to. Polaris AA isn't a single star that simply aged the normal way. It may be the leftover of a stellar collision, a merger between two smaller stars that reset its clock and scrambled its spin in the process, leaving a young-looking star wearing an old star's mass. It's speculative, but a tilted axis, an untraceable magnetic field, and an age that flatly doesn't add up are exactly the fingerprints a merger would leave behind. There's one more twist, and it has nothing to do with the star itself. Polaris hasn't always held this job, and it won't keep it. Earth's axis wobbles slowly over thousands of years, like a spinning top losing momentum. Around 14,000 years ago, the sky's pole pointed toward a completely different star, Vega, and in about 12,000 years, it will again. Polaris is a temporary appointment. We just happen to be alive during its shift. So is Polaris the most confusing star in the sky? On distance, mass, age, spin, and pulsation, working scientists genuinely disagree, and the one star we rely on to measure the universe still isn't fully measured itself. The next major data release lands this December and may finally pin its distance down for good. Until then, the steadiest point in the sky stays the hardest one to explain.